Hi Bobcats. In this video we're going to define what the pH scale is and the equation for calculating pH, and then look at how you would use that equation to find the pH of some solutions. Our objectives are to calculate the pH of a solution and to explain how pH describes how acidic or how basic a solution is. The diagram on this slide gives a lot of data points with examples showing you the pH and the pOH scale. So the pH scale is this one here towards the middle. And there's a very closely related scale known as the pOH scale, which is right to the side of it. And both of these things, pH and pOH, are directly connected to the hydrogen ion concentration in the solution or to the hydroxide ion concentration in the solution. So on the pH scale, the neutral point on the pH scale is a pH of 7. And any pH values that are smaller than 7 are considered to be acidic. Now, sometimes people will say the pH scale only goes to 0 or 1, but that's not true. For concentrated solutions of strong acids, pHs can actually have negative values. There is not a lower limit to the value that pH can take. Now, for pH values that are bigger than 7, we consider those solutions to be basic. And again, the pH scale doesn't stop at 14. It is possible to have pHs that are greater than 14. Most solutions that you're going to encounter in most laboratory experiments, however, will fall between 0 and 14. But those are not actual limits. Oh, and then if you look at all of the numbers that are in the columns labeled pH and pOH, notice the very top set of numbers is 0 and 14, then it becomes 1 and 13. I'm going to skip down a little bit here. We've got 7 and 7, we have 10 and 4, and then we're back to a 14 and a 0. There's a very simple relationship here, which is that pH plus pOH is equal to 14. That's another equation that we're going to be using a lot. And we can actually show mathematically how it's derived from our KW expression, that the molarity of H plus times the molarity of OH minus is 1 times 10 to the minus 14. To experimentally measure pH, there are a variety of options. We can have things that are called acid-base indicators, which are chemicals that change color depending on what the pH is. Red cabbage juice, believe it or not, makes an incredible pH indicator. If you boil red cabbage juice and you just take that purple reddish water that you get as a result of that, and you test it with various standard solutions, you get this incredible array of colors ranging from a pH of 2 all the way up to a pH of 11. It's wonderful. And so if you have a solution, you put some of that red cabbage juice in it, and it turns a fairly pale pinkish purple, you could conclude, the pH of the solution is 5. You can also get similar chemical compositions that have been impregnated into papers, and this stuff down here is called pH paper. And you would take a little strip of your pH paper and you would put a drop of your test solution onto the paper, and then you would see what color the paper turned, and you'd compare it to the scale that's on the container of the pH paper. There are so many different varieties of this. You want to make sure you always are comparing to the actual scale for that particular variety of pH paper. And you never want to dunk. You don't want to take that test strip and dunk it into your solution, because whatever chemicals are present on that test strip will then contaminate your solution. So you always want to do it the other way. You want to take a drop of your solution and touch that drop to your test paper. Then last but not least, we have the pH meter. In the pH meter, down here there's a probe that gets immersed into your test solution. That probe has a very thin glass bulb down at the bottom of it that's the active portion of the pH meter. Ion transfer can occur across that glass membrane, and there are wires that go down inside of that probe, and they're immersed in a solution, and based on that ion transfer from the inside of the probe to the outside of the probe, the voltage between the wires will change. That voltage is fed over to this meter, and then the meter has electronics in it that convert that voltage to an actual pH. At the top of this slide, we have the equation that defines pH. pH is equal to minus the log of the hydrogen ion molarity. Let me point out that this is log, not ln, so this is the base 10 log. On your calculator, make sure you use the log button. It's probably right next door to the ln button for natural logs that we used back in the chapter on kinetics. So to answer this question, find the pH of a sample of lemon juice which has a hydrogen ion molarity of 3.8 times 10 to the negative 4 molar. We're going to use this equation. pH is equal to minus the log of the hydrogen ion concentration. So that'll be minus the log of 3.8 times 10 to the negative 4. Now in a graphing calculator, you're probably going to type this in pretty much as written left to right. On my scientific calculator, I'm going to start by putting in the number in scientific notation. Now I'm going to hit log to take the log of that, and then I'm going to hit the change sign key since there's that negative at the start of the equation, and it gives me a pH of 3.42. So the pH of this sample of lemon juice would be 3.42. pH does not have units. We don't say it's 3.42 pH units. We just say the pH is 3.42. There's a new set of significant figure rules that we have to learn now if we're doing significant figures in logs. It boils down to figuring out how many significant figures you have in the molarity, and then that total number of sig figs in the molarity becomes the number of decimal places that we will keep in the pH. So if we have 2 sig figs in this molarity because of the 1.0, we need to keep 2 decimal places after we calculate the pH. And I snuck that in on you in the last calculation. Go back and double check, keep me honest that I really did the sig figs right on the previous one. Sometimes you know the pH, but you need the hydrogen ion molarity. To reverse engineer our pH equation, we're going to end up with the hydrogen ion concentration is equal to 10 raised to the negative pH. So for this problem, find the concentration of hydrogen ion in tomatoes, which have a pH of 4.1. We'll say, all right, hydrogen ion is equal to 10 raised to the negative pH, or 10 raised to the negative 4.1. Now, on most calculators, the key that will get you through this is the second function key on the log key. So on my scientific calculator, I'm going to type in 4.1 negative, and then I'm going to hit second function and 10 to the x. And I'm going to move that to scientific notation because it's kind of a small number, and I get let's see, 7.94328 and a bunch of other digits times 10 to the negative 5. Let's see if we can figure out the significant figures here. The way we said the rule was that the number of significant figures in our molarity is equal to the number of decimal places in our pH. Well, our pH in this problem has a single decimal place, so that means that our answer should only have 1 sig fig. So we're going to have to round it to this place where there's a 7, but the 9 that comes after it says we need to round up. So we have 8 times 10 to the minus 5 molar for our hydrogen ion concentration. In this example, we're asked to find the pH of 0.25 molar nitric acid. Now, the previous example just gave us the hydrogen ion concentration. Not so this time around. We're told the concentration of nitric acid. So the first thing you need to do is check to see, is nitric acid a strong acid or a weak acid? Well, nitric is HNO3, and that is on our short list of strong acids. So that means this is a one-way arrow, and we get H plus ions and nitrate ions. So for every 1 molarity of HNO3 on the label, we get 1 molar of H plus ions. What we started with actually was 0.25 molar. All of that dissociates, so we end up with a concentration of 0.25 molar on H plus ions as well as on nitrate ions. Think of this as being like, let me think, something that comes in two pieces. Let's say a plastic disposable water bottle. If you were to take that water bottle and take the cap off of it, for every water bottle that you have, you get 1 cap and you get 1 bottle once the cap has been removed. So if you started with 25 water bottles, you would get 25 caps and 25 bottles that have had the caps removed. All right, so to find the pH of this, the pH will be minus the log of 0.25. So I'll type that into my calculator, 0.25 log, change the sign, and I end up with 0.602059. My molarity has 2 significant figures, so that means I need to have 2 decimal places in the pH. So that will round to 0.60 for the pH of this solution. In this example, we're asked to find the pH of 1/4 molar sodium hydroxide. Sodium hydroxide is a strong base, and so that will ionize completely to give us sodium ions and hydroxide ions. So watch out, we're getting hydroxide ions, not hydrogen ions. The pH formula requires hydrogen ions. The good news is Kw will save the day, because that's equal to the hydrogen ion concentration times the hydroxide ion concentration. So we can rearrange this equation to get that the hydrogen ion concentration is equal to Kw divided by hydroxide ion. So that will be 1 times 10 to the negative 14 divided by 0.25 for the hydroxide ion. And so 1 times 10 to the negative 14 divided by 0.25 gives us 4 times 10 to the negative 14. To calculate our pH, we're going to take minus the log of H plus. And so let's see, if I take the log of that and change the sign, I've got a pH of 13.3979. I got a little sloppy on my significant figures. I had 2 in my original molarity, so I should have 2 decimal places in this number for our pH. So I end up with a final value of 13.40. In this problem, we have the same molarity, but now the compound is strontium hydroxide. This is a group 2 hydroxide, so we're going to get 2 hydroxides for every 1 formula unit, and so the molarity of the hydroxide ion will be 0.50. So when we go to calculate the hydrogen ion molarity, it'll be 1 times 10 to the negative 14 divided by 0.5. So 1 E14 negative divided by 0.5, which is 2 times 10 to the negative 14. And so the pH will be minus the log of 2 times 10 to the minus 14, which is 13.70. Our objectives here were all about pH.